All right, we're going to get started on section 9.3. This is the quadratic reciprocity law. The quadratic reciprocity law, as we mentioned earlier, has something to do with the solvability of quadratic congruence equations and the non-solvability of such equations. And it is one of the most important theorems, actually, in number theory, or at least in the elementary part of number theory. So the objectives of this section and this lecture, we're going to start with having two sort of ways of looking at the quadratic reciprocity. One, we're going to explain how the quadratic reciprocity law as a law to determine the solvability of a quadratic congruence equation mod R the primes. And this in itself, or in turn, also equivalent to, as we will see, to evaluating the Legendre symbol for A by B. All right? And we're going to explain, kind of this relationship. Then we're going to state and prove the quadratic reciprocity law, which is really not very hard. In both cases, so we're going to start with the proof of actually the second case using in terms of Legendre symbol, and then as a corollary to that, we're going to prove that how it is related to the solvability of a quadratic congruence equations. Then we're going to follow by some examples to illustrate how it applies, and then we're going to present some application of quadratic reciprocity, of determining, the quadratic character of the prime three. All right? All right, so let's get started with the explaining how the quadratic reciprocity is stated as a solvability criterion for quadratic congruence equations. So I'm going to report some concepts from section 9.1. All right, so recall, this is section 9.1. That the quadratic congruence equation, the general one, which is A x squared plus bx plus c congruent to 0 mod p, where p is an odd prime. Remember that for 2 it is not really hard. For odd prime, and we want A not to be congruent to 0 mod P. In other words, there is a square term in here. And remember also, this is equivalent to saying that P does not define that. All right, so this congruence equation, to solve it, okay, its solution is equivalent to solving or determining that, of course, it doesn't have a solution, the reduced quadratic y squared congruent to D mod P, where D is the discriminant, D is D squared, not Greek's common divisor this time, for AC, and the linear congruence equation is 2ax is plus b is congruent to y sub 0 mod p, where y sub 0 is a solution to y squared congruent to b mod. So in other words, given a quadratic equation in its general form like this, or if it is not, you could transfer it to put it in this form. And the solution of this is totally determined by solving this quadratic reduced to quadratic. Of course, if this reduced to quadratic does not have a solution, means the original quadratic congruence equation does not have a solution. Then, for each solution we obtain for this reduced to quadratic, we find the solution for the linear. Okay, and from here we find actually the solution of the original the quadratic equation. So this is what we've discussed basically in section 9.1. So of course the linear quadratic equation we talked about, this is back in chapter 4. We know how to solve these. So what remains then is actually to find a solvability criterion for this y squared congruent to d mod p. And this in itself is equivalent, okay? And so solving this, y squared congruent to d mod p is equivalent in finding the value of the Legendre simple d by p. If this is equal 1, then the equation has solution. And if it is minus 1, then d is not a quadratic non-residue, has no solution. Has no solution. All right. Now the question is how the quadratic reciprocity actually is going to do for us is the following in here. Now the d in here, as you know, it could be a prime or it could be non-prime. Now the quadratic reciprocity, actually, we're going to be able to the quadratic reciprocity law. Will reduce the evaluation, evaluation, we actually say it in theorem Legendre simple, the evaluation of Legendre simple to the special case where special case which is this Q by P for an odd prime Q distinct from also equivalent to saying that we're going to also, this is equivalent to determine the solvability of the special, again, reduced quadratic congruence x squared congruent to q mod p. So in other words, the general quadratic equation, it reduces to a quadratic equation which is y squared congruent to d mod prime. Now we are reducing it further to talking about actually where the d, or we will be looking at only x squared congruent to a prime q that is negative prime to b, means it's going to be distinct from p. All right? So that's a lot of reduction in here. So in other words, we're looking at a very special type of equation. Later on, we're going to see that once we have it for modulus that is just a prime, actually for any modulus, okay, means it could be, of course, a product of primes. Then it's going to use the prime factorization of it. Now, in this form, that is using the solvability, using quadratic reciprocity as a solvability criterion, I'm going to put the statement of the quadratic reciprocity law in this form. Okay, so here is the theorem. By the way, this theorem is not stated actually in the book, but it's nice to have it. Okay, and here it is. So this is the quadratic reciprocity. I'm going to abbreviate this version 1. Which has something to do with solvability. Or the quadratic congruence equations. Or state like this. If P and Q are distinct are the primes, then x squared congruent to q mod 3, and the other one, which is x squared congruent to p mod q, are both solvable actually we say are both are either both is solvable or both are unsolvable. Unless P and Q are both they are primes of the 4k plus f3. Or equivalently, you could say this, equivalently, D is congruent to Q, congruent to 3 mod 4. In this case, in such case, one of the congruences is solvable. And the other is not. And the other is not solvable. Now, reading this theorem, the first time, first of all, besides being confusing, it might say that, well, it's not because, this because of all these conditionals, all these restrictions we are putting in here, it's going to be of a limited use. In fact, that's not the case. All right? So let's try at least to understand this. Because I said the proof of actually the quadratic reciprocity is not hard. Understanding the meaning of it and the implications of it is what is important. All right? So in this version of the quadratic reciprocity, so we have these two special types of, reduced to quadratic congruences, and we say that if P and Q are all prime, so in order for the first portion to be satisfied in here, this means that the P and the Q are actually congruent to 1 mod 4. Okay? So if both of these, or at least one of these actually is congruent to 1 mod 4, we're going to see that both, congruences are solvable or both are not solvable. Okay? So if this has a solution, the other one has a solution, and vice versa. However, if both primes P and Q, okay, of this form 4k plus 3, all right? So in here, actually, maybe I should write it like this, because it's not both of them. P is congruent to 1 mod 4, or the Q is congruent to 1 mod 4. We're going to explain all of this. All right? So if either one of these, then both is going to be solvable or both unsolvable. However, if both of them are of the form 4k plus 3, then one is solvable, the other one is not solvable. All right? And of course, by further examination of the cases, which we know which of which. All right. So we're going to later on to prove this, but we will look at an example kind of to illustrate how this reduction, how looking at one versus the other to determine the solvability will take place. Okay? So in other words, what's the advantage, this quadratic reciprocity actually gave us to simplify the solvability criteria. Let's look at that. Again, this is a very simple example, means the values, it's going to be not very big. So here's an example. So let's consider this. And again, this is A reduced. Quadratic. So let's find the character of actually the number 5. Okay. So this is a prime. So we could think of this as like the Q in here, and think of this as like the P. All right. Now the Q, which is equal 5, actually has this form. 5 mod 103 and x squared congruent to 103 in a switch mod 5 are either both solvable or both unsolvable. Because this is not of this form. In other words, the 5 here, this is not of the 4k plus 3. So it goes under the first criterion. Now, this one is easier to work with than the x squared congruent to 5 mod 103. One of the very simple ways to actually solve an equation like this is to try the numbers from 1 to 102. Okay, just plug it in, all right, and see which one of these satisfies. However, if I do this one here, it's much easier. Also, we can even reduce this mod 5. So this is equivalent to x squared congruent to 3 mod 5. And it's very simple to determine, if this congruence relation holds. So you could try these values x equal 1, 2, 3, and 4. And none of these actually does work, so these none solve this equation. So the congruence. Even later, we're going to do something more once we start learning how to use the quadratic reciprocity in evaluating the Legendre symbol. So that's what we're going to be doing. Later on, we're going to be looking at evaluating this. What is the value? We're going to see effective methods the reciprocity law give us. But for at least, not doing much work in here, we say this is has no. Okay, none of these numbers solve the, we put none in here. None solve this congruence, which means that this one has no signature. All right. Now let's move on to the second way of explaining what the quadratic reciprocity, the significance of it, or its use, is in evaluating the Legendre symbol. All right, and this is the form actually we're going to introduce it. So the quadratic reciprocity, just give some history here. Was first discovered by Euler in the year 1783. Euler actually used experimental, in other words, experimented. In other words, just by trying different numbers and evaluating, thousands of values, then he stated the quadratic reciprocity in terms of the solvability of quadratic congruence equation. All right? But he gave no proof. Okay? No proof was given. But then it was Legendre in, again, 1785, and later on he worked on it more in 98, actually. And he gave a partial, and gave a partial proof for it. And in fact, he stated the quadratic reciprocity law in the form that we're going to state it in the next step, okay, using his symbol, the Legendre symbol. All right, but the proof, unfortunately, does have some gaps, and it uses some results which not being proved. Then it was rediscovered again by Gauss when he was 18 years old. I don't feel sorry or bad, rather. I haven't discovered anything in my entire life. Okay, so this is 18 years old and proved it and gave a complete proof, rather. A complete proof of it when he was 19. Years old. In other words, it took him about a year actually to do the proof. And this is a great Gauss, okay? And actually he writes in his note how much torture actually the proof actually gave him. But later on, before Gauss died, he gave another 7 proofs of this quadratic reciprocity. Now, the number of proofs that are actually available for this, because it's such an important result, is about 200 so far, okay? Now we're going to present the proof that actually one of Gauss's students gave. His name is Einstein, all right? And the proof is very simple, very transparent. It uses a geometric argument and easy to understand. All right, now we are ready to actually state and prove the quadratic reciprocity in the form that Legendre stated it. But that's the proof we will give, is not Legendre's proof, because his proof was incomplete. But we will give a complete proof. And this is also based on Gauss's actually lemma, what's called Gauss's lemma. But here is the theorem that corresponds to this in the book. Theorem 9.9. And this one is as stated by Legendre. In 1798. In fact, Legendre was very upset because the law is they refer back to it as Gauss's law, and he rediscovered it, or without knowing, of course, Euler's work, and nobody gave a credit for Legendre, at least in the days of Gauss. Did not make him happy. So this is actually what we're going to call, this is the second version of the quadratic reciprocity. The first one has to do with the solvability of the quadratic congruences, this one in terms of Legendre's symbol. And it reads like this: if P and the Q are distinct odd primes, then the Legendre symbol P over Q multiplied by the Legendre symbol Q over P. And you can see that is why we call this is the quadratic reciprocity, because we're going to be invariant, it's like reciprocals. We can take reciprocal of the, the Legendre symbol. And this is actually equal -1 to the exponent of P minus 1 over 2 multiplied by Q minus 1 over 2. All right? And of course, we're going to be stating some corollaries to this, which make even this one, we could write it in a variety of ways. All right, here's the proof. We're going to apply, Gauss's lemma, second version. Which says that Q over P, this one is equal to -1 to the exponent R, where R is the summation of K equal 1 to Q minus 1 over 2 of the greatest integer of Qk or Kq over P. All right, and similarly, we have P over Q is equal -1. And let me use this exponent here is M, where M is equal to a similar summation, P equal 1 to P minus 1 over 2, bracket Kp over Q. All right. Now we're gonna employ a geometrical argument. So we're gonna use apply a geometric argument to evaluate R and M, of course, in terms of P and Q. So we're going to express these in terms of P and Q, and then we're going to plug these back in here and see that actually this formula holds. To do this, we're going to start by looking at constructing a rectangle in the first quadrant of the xy plane. And we're going to count the number of points inside this rectangle whose both coordinates, the x and the y, are integral values. Because such points, lattice points. Okay? So we're going to consider the rectangle OABC. Yeah, let me actually put the rectangle in here, and then this way we can label its vertices. All right. O is, of course, the origin its coordinate is going to be p over 2, 0. This is on the x-axis. And then the y up here, it's going to be, this point is, we're going to call it actually c. And this is going to be 0 and the q over 2. And then the b is going to be this point, whose coordinate is p over 2q over 2. And remember, the p and the q are distinct, so this one is not going to be a square, it's going to be actually a rectangle. All right? So where the of an emphasis O is 0, 0, A is P over 2, 0, B is going to be 0, P over 2, Q over 2, and the point C is 0, Q over 2. Let me define this concept. So we call a point x, y, a lattice point if both x and y are integers. Of course, in our case, they're going to be positive integers because they are interested in the points inside actually the rectangle. But this concept actually works for other types of points, which we call lattice points. All right. Now, let's look at the equation of the diagonal in here, which goes from O to B. So the equation of the diagonal OB is given by this. Y is equal to Q over P times X. It has a y-intercept of 0, and the slope of this, which is the rise, which is a Q divided by the, or Q over 2, if you wish, divided by P over 2. So this is what we get. Now, since the slope which is equal to Q over P is in its lowest terms, because there is no common factor between Q and P, its lowest terms, then for any value of X, such that X ranges through that rectangle from 0, all right, to P over 2. We don't want to include 0, of course, we just want to look at what's in between. Y is not going to be an integer, basically. Y is not an integer. And this implies that none of the points of the diagonal are lattice points. This implies none of the points on the diagonal from OP are lattice points. All right, because to find a value for y, you need to multiply the q over p by a number less than p over 2. So you cannot cancel basically the T. All right. So, and that's going to be actually non-integer. But now we're going to divide this rectangle, into two triangles. And we're going to count the number of lattice points inside these two triangles, because these are the only lattice points. Because if there is none on the, and inside, I don't want to consider the boundary, only inside the rectangle. All right? I want to call the lower part of the rectangle T1, and this is T2. All right? Now I'm going to take a value for x. In here, I'm going to consider all the points on this vertical line. All right, so we're going to take x equal k. And then I want to count the number of lattice points that are in the rectangle at the same time are in T1. Okay? And then I'm going to do the same thing in here by considering horizontal lines. And we're going to come along the horizontal lines. So the argument goes like this. So we're going to let k be an integer. As you see, it is indicated in here. It is picked up from between 0 and t over 2. Okay? These are such that one less than or equal k, less than or equal t minus 1 over 2, or less than t over 2. Okay? Because t over minus 1 over 2 is an integer, so it's a legitimate value to be inside. And we're going to look at the number of lattice points. So the number of lattice points on this vertical line whose equation is x equal k. All right? And I want this one to be inside T1. All right? So for a particular one, we're going to go just, remember that the equation of this diagonal is y equal q over p x. So one of the highest value is when I get x is equal, when you plug in here k, and you want the highest integer that is actually less than or equal p over or q k over p. Okay? So in other words, we're going to count these, all right? And so so we have this one. All right, and this one, inside this one, it's going to have y coordinates that satisfy this. The y, again, is going to be actually bigger than, because we want it inside 0 and less than q k over p. So the x is fixed. So as far as the y is actually smaller than the last point, which is going to be on the diagonal, all right, which is going to be here, all right. So the number of such integers here on the vertical line, again, x equal k, is the greatest integer of this. Okay, that is the largest without actually equal to the point which is not integer, okay, on the diagram. All right, now the total number of lattice points inside the rectangle T1. So this is only counting the number on one vertical line. Now we're going to consider all vertical lines, of course. So for each k equal 1, we're going to have 1, so k equal 2, another one, and so on. All right, to the last one, which is t minus 1 over 2. All right, so this implies that the total number of lattice points inside T1 is the summation of expressions like this over P, where the K ranges from 1 to P minus 1 over. Similarly, we're going to do for similarly, we need to count lattice points inside T2. And the way we do this one, we're going to consider horizontal lines this time. So we're going to repeat basically the same argument. So we're going to consider here instead of k, let me use L here. So let's take here y equal to, I think I actually want to take j. All right? So we're going to, for every j, and this is between q minus 1 over 2 less than q over 2, and this is bigger than or equal to 1. All right? The horizontal line which is y equal j, has lattice points, or has the x values for it, has x coordinates, and that satisfies this. So the x is going to be bigger than or equal to, let me make it, this is greater than or equal to 0 in here. And the other end is going to be, we're going to solve this actually for x. So we're going to write this as x equal p over q y. All right? So this one is going to be p over q j. So for each j, we're going to have an x value. So this one is going to be the points going horizontally this way. And the number of the lattice points in here is going to be just the largest number less than or equal to this p over qj. All right? So the number of lattice points and such a horizontal line is this for every j, all right? So this is for every j is given by this horizontal line is going to be bracket J times, this time we're going to have times P. So this is J P over AQ. All right. So it's similar to this, again, the same thing. Now with this, then we can say what is the total number of lattice points inside T2. So we have the formula for T1, and then similarly we have the total number. And remember this one, according to our, during this was R, okay? And here also the total number of lattice points inside T2 is equal J equal 1 to Q minus 1 over 2, then the bracket J P over Q. Now the sum of these, remember we had then, and this is equal M. So then the total number of lattice points inside the rectangle OABC is R plus M, which is, we could write it also in terms of this formula if you wish. We really don't need to. 1 to P minus 1 over 2 KQ over P plus summation J equal 1 to Q minus 1 over 2 of J P over Q. Now we're going to do the counting in a different way. A different way is, we know how many integers in the interval from 0 to P minus 1 over 2. All right? Because the last one in here, P over 2, is not an integer. And there are a P minus 1 values in here, P minus 1 over 2. And vertically, there are also the length of this as the integral value of it is going to be, again, Q minus 1 over 2. On the other hand, using a different counting, on the other hand, the number of lattice points inside the rectangle OABC is equal P minus 1 over 2, that's the number of integers along the x-axis, multiplied by Q minus 1 over 2, which is the y-axis. Now, these two must equal. So this must equal R plus M. Now, going back to the original statement that which Gauss's lemma tells us. So we have P over Q. And actually, I wrote it maybe Q over P first. I don't know which way. Maybe. Yeah. P over Q. This was minus 1 to the M plus R or R plus M. And now we can separate this, of course, and replace it. The M plus R is by the P minus 1 over 2 multiplied by Q minus 1 over. All right, well, that is very good. That's the proof. This is it. Okay. Now we can actually simplify this formula and write it in two different forms. All right. And we will see that it will make even the calculation easy. All right. All right, so let me give two corollaries that we can use to evaluate the Lejeune simple. So this is corollary 1. Again, we're given that P and Q are distinct prime on then E, Q, Q, E is equal 1 if P is congruent to 1 mod Q, or Q is congruent to 4, sorry. 4, or Q is congruent to 1 mod 4. And it's equal negative 1 if P is congruent to 3 mod 4, subprime 4, but here is N. The Q is congruent to 3 mod 4. What am I saying in here? Yeah, Q is congruent to 1 mod. Well, let's look at actually the proof of this. If P is congruent to 1 mod 4, this implies that P is equal 4K plus 1 for some K. And or if Q is congruent to 1 mod 4, this makes Q is equal for K prime, plus 1 for some K. Now let's look at actually what the quadratic reciprocity saying that P over Q times Q T, this is minus 1 to P minus 1 over 2 times Q minus 1 over. Now for these we have the P minus 1 over 2 is going to equal 4K plus 1 over 2 minus 1, which is equal to 2K, which is even. All right, and regardless what the Q is, this, this exponent is going to be even, or on the other hand, regardless of the other one, or we're going to have the Q minus 1 over 2 is actually also 2K prime, which is even. So in both cases, we're going to have the exponent is an even exponent, And this is going to give me 1 as the corollary is stating that we should get. So therefore, the P over Q on P is equal -1, 2, and even exponent, and this is positive. On the other hand, if P is congruent to 3 mod 4 and Q is congruent to 3 mod 4, this makes the P minus 1 over 2 equal to 3K, make that 4K, plus 3 minus 1 over 2, and this is going to be 2K plus 1, and for the Q minus 1, similarly, it's going to be 2K prime plus 1. So both of these are odd, and their product is odd, and we end up with the -1 raised to an odd exponent, and this gives me -1. So therefore, P over Q over P is going to be -1 to P minus 1 over 2, Q minus 1 over 2, and this is odd, and this is negative. Another corollary of this corollary, actually, where we could express, and that's the one before we're going to be most often used, right? One of these Lejeune simple in terms of the other, right? So this is the corollary to same assumptions, P and the Q are distinct, odd primes. Then we have P over Q is equal to Q over P if P is congruent to 1 mod 4 or Q is congruent to 1 mod 4. And it's going to be negative of the Q over P if P is congruent to 3 mod 4 and this is all, this is and the Q is congruent to 3 mod 4. Okay, let's look at the proof. We know that P over Q, Q over P is equal to 1. This one is if P congruent to 1 mod 4 or Q is congruent to 1 mod 4. This is from the previous corollary. So under this assumption, I'm going to multiply both sides of this by Q over P. Okay, so I'm going to multiply both sides by Q over. Remember, Q over P is equal to 1 or -1, so we multiply by a number. And this implies P over Q, Q, P, and the Q. and this becomes just a Q here on this side. Now the Q over P, this is the same as Q squared. So this is P over Q, and this is Q squared. But the Q squared P is equal 1. This is property of Lejeune simple, so which makes the P over Q is equal to Q over P. So this is equal 1, and we are done. Let's look at the other case. So that is, as I said, the way we're going to be using this, because what we're going to be doing is we're going to be switching the P and the Q to make almost the denominator actually small, because we're going to do mod then. And by doing this, several times we're going to see that actually it will reduce evaluating the Lejeune simple to basically a few values we need to know. And from these data, we'll be working with this the next. Once we're done with this corollary, we're going to see how this actually will work. So let's look at the second case, that is P is congruent to 3 mod 4, and Q is congruent to 3 mod 4. From the previous corollary, we said that we have the P by Q and the Q by P. This one is equal -1. All right. Again, we're going to multiply both sides of this by the Q over. Yeah, when I do this one, we end up with on the left side just P over Q, the square is going to be equal 1, and then we get Q over. All right. Now, let me actually, before I give examples and so on, prove the first version of the quadratic reciprocity as a criterion for solvability. Okay, so we're going to prove the very first theorem that I stated. Okay, so it is the proof of the theorem, which is a quadratic reciprocity version 1. So remember that it refers to these two special, so the quadratic congruences, x squared congruent to Q mod P, and x squared congruent to P mod Q. All right. We're going to find out both of these are if either P is congruent to 1 mod 4, or the Q is congruent to 1 mod 4, then both equations either has solutions or both equations has no solution. All right. Now, remember when we have this, then this implies by corollary 2 so let's see, would we want corollary 1 or 2 in here? All right, let me actually use corollary 1. By corollary 1, we have P over Q times Q over P is equal to 1. This is true if and only if both of them are equal to 1 or both negative 1. To multiply two integers to come up with a positive 1, or P over Q is equal to negative 1 and the Q over P is negative 1. Now, if the first case happens, then means both are solvable, right? Because the quadratic, the Legendre simple, that's what it does indicate. If, so therefore, if P over Q is equal to 1, this implies x squared congruent to P mod Q as a solution, and Q over 1 P equal 1 implies x squared congruent to Q mod P as solution. Well, the other scenario is when both have equal negative 1, if P over Q equal negative 1, and we put them in one line here. Q over P is negative 1. This implies x squared congruent to P mod Q has no solution, and x squared congruent to Q mod P has no solution. Okay, each one corresponds to these equality. Similarly, for the other case, that when we have P and Q, again by the corollary, if P is congruent to 3 mod 4, and the Q is congruent to 3 mod 4. Remember the corollary said that corollary 1, we have the P over Q times Q by P is equal to negative 1. But this happens to be negative 1, this implies P over Q and the Q over P. One is going to be equal 1 and then the other equal negative 1. This one have opposite signs. What does this mean? Means have opposite sign. Means one is, if P over Q is -1, 1, let me so 1 is, all right, this one, the Q over P is going to be -1, and this means X squared congruent to P mod Q. This has solution, and then the other one has no solution. And X squared congruent to Q mod P has no solution. And in the other scenario goes the other way around. All right. So this actually does take care of the quadratic reciprocity in terms of solvability. All right. Actually, let's look at a general discussion first about evaluating the Legendre simple, and then how this quadratic reciprocity would actually reduce it to know the Legendre simple basically for how many values? 3 values. 1. Now we need to consider the how to find method of evaluating the Legendre simple A by B, where A does not equal plus minus 1 because we already done those, all right? It's an integer. And P is an odd prime. Of course, relatively prime to prime, and P does not divide. The idea is this. So we're going to write A, that A equals plus minus, could be positive, could be negative integer. Let me see what kind of exponent what it is. K sub 0, P1, K1, P2, K2, P R, K sub 1, where the K sub I, this one is bigger than or equal to 0 for every I, from 0 to R. And then PIs and 2 are distinct. In other words, this is the prime factorization. Okay, so this is the standard prime factorization of A. Now to find A by P, because all of these are relatively prime to each other, all right? Actually, they don't need to. The Legendre simple is actually completely multiplicative. So this one is going to be plus minus 1, all right? Then I can take the 1 by P, and then we can take 2 by P and raise this to the K sub 0, and P1, P, K1, and so on. E sub R to the K sub R. We already know the values of these. Okay, we have these earlier. Okay, which the 1 is equal 1 minus 1. There is a formula for that, and the 2 also there is a formula for this. In fact, the one which we're going to be using more often is for this one. This is -1 to b squared minus 1 over n. All right? And this one, I forget what is the -1 over p it's given by, but there is a formula for that. I don't have it in here. But anyway, so in order then to evaluate the Legendre simple, we want to be able to evaluate this p1 over p. So what is we left with? So the problem of evaluating, as you see, in other words, we need only to plot. So to evaluate a over 2, we only need to be able to evaluate this 1 over p and 1 over p, 2 over p, and the q over p, where q does not equal p is an odd product. Now, this is where the quadratic reciprocity is going to be applied in evaluating this. Okay? So we use the quadratic reciprocity to evaluate q over p by by replacing the Legendre simple by the Legendre symbol of smaller denominator, all right? By continuing what we sometimes call inversion, means flipping things, and division, means doing mod arithmetic to make the denominator is 4. All right, this is stoking, means it's not going to, we need to explain what in the heck this means. So once we do this, we're going to arrive at any q over p is going to be reduced to one of these 3 cases. In other words, by keep doing inversion and so on. Because remember that every number we can actually divide it to find a remainder of 2. All right, by successive division. All right, so let's look at an example actually how this works. So here's an example, and I want to take an example I took from the textbook. let's say we want to evaluate, and remember evaluating Legend simple is equivalent to solving x squared or determining whether x squared congruent to q or an integer in general mod p. All right. So let's evaluate this Legend simple 29 by 53. All right. First of all, we have the 29, in fact, is congruent to 1 mod 4. All right, which means that this one is going to be actually both of these, and also have 53 is also congruent to 1 mod 4. So this fits into the product of these is going to be actually is equal to 1. But we want to see this through the reduction. So let's go with 29 over 53. Actually, this is we're going to apply the corollary 2. Remember that corollary 2, go back in here to express one in terms of the other. So this one is equal to 53 over 29. So we have a smaller denominator. And now I can see this is equal to, because we're going to reduce, we have 53 is congruent to 24 mod 29. So when we take the Legend simple, remember that if A is congruent to B mod prime P, this implies that A over P is equal P over P. So we're going to be using this theorem to say that this one we can reduce to 24 by 29. All right? And also we can write this, which is going to put actually equalities between these. Okay? Not congruences, but they will be equal. All right? Now then we're going to take this to be the product, or we're going to break this into 2, 29, then 3, 29, and 4, 29. The last one in here, because this is a square, so this is equal 1. Then we have 229 and 329. Now we're going to flip again. So in here, we can say this one is, because again, the prime 29 is 1.4, by the same corollary, this is 29 over 2, and this is 29 over 3. And now 29 over 2, this one reduces by subtracting a 28. So this gives me actually no, actually, in the book they are using for this one, for this one, we can actually use that because of 29 is of the form congruent to 1 mod 4. This is equal -1. And stop this one. All right. So in here we're going to be using actually theorem 9.6. All right. In it gives us how to find the quadratic residue of 2 mod a prime. 29, as you know, this is congruent to 5 mod 8. And this, by this theorem, implies that 2 over 29 is actually equal to -1. All right? So we have this is -1, then we have 3, 29. Now, as I said, we're going to reduce everything to either 1 over p over 2 or -1, 1, and 2. All right? Now, let's look at the 29. We're going to do the same thing. We're going to be using the same theorem here. So this is actually equal -1. And then I'm going to flip the 29 over 3. And again, will be the same because 29 is congruent to 1 mod 4. So just replace it by invert. All right. Now, similarly, we have to evaluate this. We're going to reduce this. So this is -1, and this becomes 2 over 3. Removing 27 out of it. That's 27 is actually congruent to 0 mod 3. All right. So 29 becomes congruent to 2 mod 3. Now, again, 3. By the same theorem, 6.9 is congruent to 3 mod 8. And again, will give us the value of 2 over 3 also to be -1. So this one is going to be -1 times -1, and this is +1, which we already know from the very beginning, but we just want to see how actually this would work by, evaluating using the quadratic reciprocity. All right. Another application I want to look at is to find remember one of the two fundamental problems of quadratic residue theory is determining what the primes, given an integer a, to find all the primes that a is quadratic congruent to, quadratic residue of, or quadratic non-residue. And this is equivalent to find this, all right, to evaluate three IP, where P is an odd prime, does not equal to 3, is an odd prime. All right. Again, we're going to look at by corollary to there are two cases to consider, depending on the form of P. Case 1, where we have P is congruent to 1 mod 4. In this case, then we have 3 IP is the same as P5. Now, for this one, find P by 3. Again, you need to consider P is congruent to 1 mod 3, and in this case we have P by the 3 is the same as 1 over the 3. Because we are doing mod 3, since these are that one. And 1 by 3, of course, is equal 1. Then the other type of prime P has is this, congruent to 2 mod 3. And in this case, P by 3 is equal, actually, 2 by 3, like this. And the 2 by 3, this is equal negative 1. We just actually see this a minute ago. All right? Therefore, we can conclude out of this that when P of this force, okay, and we have either 1 or negative 1 for this, so this is equal 1 if P is congruent to 1 mod 3, and we get negative 1 if P is congruent to negative 1, sorry, 2 mod 3. All right? Now, let's look at the second case, all right? Let me actually leave this here, because I need this information. When I look at the second case, case 2, when P is congruent to 3 mod 4, then 3 over P is going to be negative P over 3. And by the same scenario here, this is going to give me 1 when we have a negative 1 and negative 1. All right? So this one is going to be 1 if P is congruent to 2 mod 3. We can flip. And this one is going to be negative 1 if P is congruent to 1 mod 3. So all together we can put them in 1 4. So putting the two cases into this. So 3 over P is going to equal to 1 if this condition is satisfied, if P is congruent to 1 mod 4, that's from case 1. And to get 1, we need also P to be congruent to 1 mod 3. And P is congruent to 1 mod 3. Or there's another possibility where P is congruent to 3 mod 4 and P is congruent to 2 mod 3. So any one of these two cases is going to give me 1. Then the negative 1, when P is congruent to 1 mod 4 and P is congruent to 2 mod 3, which is this one with 1 in here, so add 1. And the second scenario is when we have the P is congruent to 3 mod 4 or Okay, so these together give me 1, and these together is going to give me negative 1. The or in here, P is congruent to 3 mod 4, and P is congruent to 1 mod 3. Well, we could actually reduce this. We can apply the Chinese remainder theorem. Apply the Chinese remainder theorem. To make this mod, to put in mod 12. Which is the product of a 3 and 4. So to convert to mod 12. So how we do this? We're going to be basically solving this congruence equation. So we're going to solve this system. Okay, P congruent to 1 mod 4 and P congruent to 1 mod 3. So we're going to apply the Chinese remainder theorem to this system of congruence equation, and this gives me, okay, we put the resultant here. This gives P congruent to 1 mod 12. Going to apply the Chinese remainder theorem to find this. And in the second pair, which is P congruent to 3 mod 4, together with P congruent to 2 mod 3. Again, the Chinese remainder theorem gives this solution. P is congruent to 11 mod 12, or this is equivalent to P is congruent to negative 1. So you could reduce it in a different way to 12. Then we're going to do the same thing with the first, with this one, this system. This one is going to produce P by the Chinese remainder theorem 5 mod 12, and this one is going to give us solution. This is congruent to 7 mod 12, and the 7 mod 12 actually also is congruent to negative 5. So P is negative 5 mod 12. So the 7 and negative 5 are the same. So all together, when I put this together, we have actually a theorem which gives us the quadratic character of 3. It tells us which primes the 3 is a quadratic residue of, and which one are quadratic non-residue. So I've got the same formula for like 2P. Okay? So here is the summary of all of this. So this is Theorem 9. No, this is 9, 10. I'm not mistaken. 9, 10. And this goes like this. If P does not equal P is an odd prime, then 3 by P is equal to 1 if P is congruent to either plus 1 or minus 1 mod 12, and negative if P is congruent plus minus 5 mod 12. All other types of primes mod 12, or all other number mod 12, actually they are not going to be primes. Only this one, all right? In other words, b plus b is congruent to 2 or 3 or 4. All of these are not the primes. Okay, so these are the only mod 12 primes. All right. We have one last, actually, application of, which is an example of quadratic reciprocity, has to do with primitive roots. All right, so this is the last example in the textbook. First of all, let's recall what we've done in section 8.1, actually page 150. We have shown if the Fermat number Fn, which is equal to the power 2 to the n plus 1, is prime, then 2 is not a primitive root. Not a primitive root of Fn. So we have a negative, result for the 2. Now, we apply the quadratic reciprocity to show if Fn is a prime, then the 3 is a primitive root. Of Fn. All right, so this is our objective, and this example is to show that actually 3 is a primitive root. Now, to do this, first what we need to show, this is equivalent to showing so to show 3 is a primitive root of n is equivalent to show the order over 3 mod Fn is equal to Euler's phi function on Fn, and since Fn is a prime, this means this is Fn minus 1. And this in itself means we have to show that the 3 to the phi of Fn is congruent to 1 mod Fn, and the 3 to the k is not congruent to 1 mod Fn for every k less than k of n. There is no small prime to this. Oh, so this is keep in mind. That's what we would like to get to. All right? Now, to achieve this, first we're going to because we want to be using the Legendre symbol for, basically we're going to be, to use the quadratic reciprocity, we're going to be evaluating this. So we need to evaluate it. And remember from the form that we have the value of this is based on mod 12, all right, form of the Fn, all right? So I want to claim that Fn actually has this form. 2 to the power 2 to the n plus 1 has this form. The form, actually 12k plus 5. And remember, this gives us the value of -1 for this. All right? And to do this, we're going to do a, kind of something looks like maybe unrelated, but we're going to see it will be actually what we will be using. Is first, we show 4 to the m is congruent to 4 mod 12 for every m equal 1, 2, and 4. And this one we're going to do it by induction. On m. So let's just start with m equal 1. Very simple induction proof, actually. For m equal 1, we have 4 to the 1. Yes, it is congruent to 4 mod 12, because we get difference of 0 this one. So let's assume induction hypothesis congruent to 4 mod 12 for some m bigger than or equal to 4. And let's consider 4m plus 1. Well, this is equal 4 to the m multiplied by 4 to the 1. But 4 to the m is congruent to 4 times 4. Well, the 4 to the m is congruent to this, and then the other 4 mod 12. So this is congruent to 16 mod 12. This is a 12, supposed to be here. Mod 12. And once again, this is congruent to 4 mod. So yes, it does hold. Which means that by induction hypothesis, the statement is true, all right, for every m. The net result, yes, we have, therefore, 4 to the m is congruent to 4 mod 12 for every m bigger than or equal to 12. Now let's look at the Fermat number Fn equal 2 to the 2 to the n plus 1. And we can write this as 2 multiplied by 2 to the n minus 1 plus 1. Now I want to take 2 to the 2 in here as 4 to the 2 n minus 1 plus 1. Or I could call this is m. All right, and we just showed that this one is always congruent to 4, and then we have plus 1 mod 12. So it makes that this one is congruent to 5 mod 12. and disproves the claim. So therefore, if n has the 4, 12k plus 4. Now, let's look at the Lagrange symbol for 3 mod Fn by the previous theorem, 9, 10. Therefore, we have 3 by Fn is going to be equal negative 1. Since Fn has this 4, or Fn is actually, we put it congruent to on F5 mod Fn. Mod 12, not Fn. All right, well, now let's apply Euler's criterion. We have 3 by Fn. This is congruent to 3 mod phi of Fn over 2 mod Fn. And this in itself, of course, is the same as 3 Fn minus 1 over 2 mod Fn. All right. But this one, remember also this one in here is congruent to negative 1. So this means that we have a 3 Fn minus 1 over 2 is congruent to negative 1 mod Fn. So this is what we conclude. Now we're going to square both sides of this. Because if these are congruent in to any power, square both sides, they will be congruent. And this gives us the potential of, this is congruent to 1 mod Fn. Or equivalently, this means that 3 to the phi of Fn is congruent to 1 mod Fn. So yes, it looks like the order of a 3, it's going to be getting close to equal to the Euler 3 function. Now I want to show that there is no smaller exponent than phi of n that gives us 1. All right? And to do this, also need a little argument. Now let's assume that the order of a 3 mod Fn is equal to k. Where we're going to also assume that where k or then k is actually it's going to divide, okay? This implies k divides field of Fn. And I want to assume it's actually a proper divider. We can assume that k is smaller than. So this is going to lead to a contradiction, of course. You're going to see that the k must actually equal that field. Well, let's see what does this mean. This means K divides phi of Fn, which is Fn minus 1, which is 2 to the power 2 to the n, which makes so this means that actually 2 to the power 2 to the n is equal K multiplied by m for some even integer m. Because remember that we have the K is actually smaller than Fn, so this one must be actually bigger than 1, so it must be actually an even number, all right? Because the left-hand side is all, primes 2, or powers of 2, this is the prime factorization is powers of 2. All right, now let's divide both sides of this by 2. This would imply 2 to the power 2 to the n minus 1, divided by 2, using the exponent by 1, is going to equal k m over 2, which is equal k m prime. But m prime is m over 2 because it's even, so this is a legitimate integer. This implies that k is going to divide actually 2 to the power 2 to the power n minus 1. All right? Well, let me write this down up here. Let me leave all of this information in here. So we have the last divisibility is k divides 2 to the power 2 n minus 1. All right? But this is equal actually phi of Fn. All right? Over 2. All right. So altogether, then we can say that phi of Fn over 2, which is equal to k, this is the same as k m prime, remember this? And now, which is the order according to our k is the order with 3 times m prime. Well, let's look at the 3 to the k. This is congruent to 1 mod Fn. And this implies we're going to raise this to the m prime for 1 m prime mod Fn. But this last relation, we can write it in terms of the phi of Fn over 2. So this one is a 3 of phi of Fn over 2 is congruent to 1 mod Fn. But we have from the very beginning, and this is equal to, remember that this one was equal to the 3 Fn. and this is equal -1. So we have a contradiction in here. So this implies -1 is actually congruent to 1 mod Fn. And this is a contradiction. All right? Which means that we cannot have K is less than. So K must equal to the field of N, or the order of, therefore, the order 3 is equal K must equal the field of N, and this makes the 3 is a primitive root of F. And this concludes the proof. All right, it's a little long lecture, but I just want to finish it up. Okay, so we have one more section on this chapter. I'll be doing this, I hope, tomorrow.